Of crystalline solids by Dr. Mandeep Singh Bakshi.
Good morning. We are going ahead with the next lecture. So this is quantification of crystalline solid. You will you will see that during the course of the lecture series, we initiated our discussion from the solution properties, and then slowly we are shifting our our attention to the solid state. The reason is that because the system we are focusing on, so that is the combination of both aqueous and the solid phase. You could see it is the iron oxide nanoparticle for biomedical application. Eventually, our aim is to understand that how iron oxide nanoparticle exist in the aqueous phase. It means that practically we have two components. The one is the aqueous phase, and other one is the solid phase. The solid phase exists in the crystalline form. So now it means that we must understand appropriately what is the meaning of the aqueous phase on which we are concentrating, and what are the physiochemical properties and how we can characterize the aqueous phase and its characteristic properties quantitatively. And the second aspect of this whole series of lectures is the solid state. We have arrived over here from the fundamentals of the aqueous phase, where we are quantifying the concentration scales in terms of molarity and molality, and eventually we have explained all the physical properties of the aqueous phase in terms of solute dissolves in the solvent. Now then, we slowly shifted to the microcrystalline phase that exists in the aqueous phase, and I told you that that is the synthesis of the nanoparticle. So for the synthesis of the nanoparticle, colloidal stability is required, and for the colloidal stability, we need to focus our attention on the amphiphilic molecules, and thereby we talk about the surface active molecules or the surfactant and their properties. Now we are going to combine all the different fundamental aspects on the objective of our GAN program. So that is the iron oxide nanoparticle and their bioapplicability. So during the course of this information or the lecture series, now we will try to understand that what is the meaning of the solid phase and in which solid phase we are interested. So the solid phase in which we are interested, that is the crystalline solid. What is the meaning of the crystalline solid? I cannot directly take you to the iron oxide crystalline nanoparticle unless you understand what is the meaning of the crystal and what is the meaning of the solid state when we deal with the crystals. To begin with, first we need to differentiate between the crystalline solid and non-crystalline solid. The crystalline solids are those solid materials or those solids which have the long range order. What is the meaning for that? I mean to say that a crystal is in which the component of the crystal, so they have the repeated order in 3 dimensions along the x-axis, y-axis, and the z-axis. So if you take any fraction of the crystal, you will see that the component of the crystal's composition remains constant. So that is the meaning of the crystal. So it is a well-defined 3-dimensional order of the components which constitute the crystal. In contrast, amorphous solids, that is not the case. Though amorphous solid could be made up of only one kind of entities, those may be in the form of atoms, molecule, or any other form of entity. They do not have a long range order. The long range order means, suppose if I'm saying that this is a solid substance, and you will see that if I'm going to talk about this entity, it could be atom, molecule, or anything. So you will see if I am moving in any of the three dimensions, x, y, and z axis, you will see exactly the same pattern running across the three dimensions. That is not the case of the amorphous solid. So in the case of the amorphous solid, this kind of regular arrangement is disturbed immediately as you try to move either along the x-axis, y-axis, or the z-axis. So therefore, there is a contrasting difference between the crystalline and the amorphous solids, and the repeating units which repeat in three dimension, they are known as the unit cell. Is the basic repeating structure of a crystalline solid. So in the case of amorphous solid, we do not have such kind of entity which could repeat in three dimension. But in the case of crystalline solid, so this is the case. Why we are more interested in crystalline solids? The reason is that the nanoparticle uh, on which we are interested, they may be the gold nanoparticle, silver nanoparticle, or iron oxide nanoparticle. They are all in the crystalline phase, not in the amorphous phase. It means the focus of our course is to deal with the nanoparticles, those possess exactly the crystalline phase rather than the amorphous phase. Uh, what is the advantage of the crystalline phase? Slowly, I'll explain that why we need the crystalline phase in comparison to the amorphous phase. Okay, going ahead with this, uh, this is the simple fundamental understanding that how many kinds of the unit cell exist. So you already know about this, but I'm just refreshing your idea. So it's a simple cubic, unit cell, tetragonal, orthorhombic, rhombohedral, and so on. But the unit cell, which we will try to understand appropriately, quantitatively, that is the cubic unit cell. So therefore, the first unit cell, simple cube or the cubic, our explanation in this lecture will focus only on the first unit cell. So these are the characteristic properties that what should be the edge length or the three dimensions of the unit cell, if they are equal or not on the basis of that, as well as on the bond angles for all the three sides and how they vary from one unit cell to another unit cell. So on the basis of that, we name the unit cell. What is simple cubic unit cell? So simple cubic unit cell is uh, it is it is the arrangement of the atoms. You may consider there is a one layer of the atoms, and there is another layer of the atom where one atom is exactly placed on the layer of another atom, and this repeating unit repeats along the x-axis, y-axis, and the z-axis. Now, if you only pick the 8 atoms, because it is repeating in three dimension exactly in the same way, so therefore we are picking the smallest repeating unit. The smallest repeating unit is the eight atoms among any adjoining layers, along the x-axis, y-axis, the z-axis. If you pick 8 atoms, 4 from the above layers, 4 from the lower layer, and concentrate on the center of the atom. This is the center of this atom. This is the center of this lower front atom center. And these are the corners, means these are the points which represent the center of the atoms which are on the behind these two atoms. So this is the center for this one is for this one, and the same is the story for the lower atoms. In this way, if I'm going to draw a line among all the centers of the 8 atoms, I'm going to produce a cube. You see that because all atoms are identical, so therefore all sides of the cube are identical, that is the length, width and the height, they are all identical, and because they reside exactly one above the other and their sizes are equivalent, so therefore the bond angles as well, they are equivalent. So all bond angles are 90-degree bond angle. You assume that this cube is in the form of a sharp frame, razor sharp frame, and if I want to hold the sharp frame and snatch it out, then some part of each atom is going to be included in the cube, and that is the part of this atom, and this is for the this one, and this one for this one. And this way I mean to say that when I'm going to take out the frame, the cubic frame, that is a razor wire sharp, so it is going to slice each atom and it will take away some part of the each atom. So it means that you would see there are 8 parts of 8 atoms. You see this part, this much part is included in the cube. Likewise this part, this part, this part, and same is the story for the lower 4 atoms. Now, what is the meaning for this? We are trying to understand that what is the meaning of this. This is in fact the unit cell, right? The unit cell is the one that is repeating. So it means that this is the unit cell which repeats itself in 3 dimensions. Anything outside the unit cell we are not considering for the time being. As you could see, basically we have drawn the cube, we have drawn the unit cell by taking the center of each of the atom. So therefore, a greater amount of each atom resides outside the frame. But we have, because the definition of the crystalline solid is that there is a unit cell and that unit cell repeats itself in all 3 dimensions. So therefore, exactly this is the unit cell which is repeating in the 3 dimension. How we can quantify this? See over here. We have a few more definitions. Means, do we have only one kind of this cubic structure? What if we can there could be another atom where there is a space, you see the intervening space, empty space over here or over here, that empty space can also be occupied by an atom. If that is the case, means you could see that if I'm going to place the atom over here, I mean to say that there is empty space. If I could insert the atom over here, then the definition of the unit cell changes. It still remains the cubic unit cell, but now the definition is body-centered cubic unit cell. In the body-centered means there is one full-fledged atom that is present in the center of the unit cell. That is why we name it body-centered cubic unit cell. What if, because we have the space over here, we have the space over here, likewise over here, front and back. Instead of inserting exactly over here only one atom, but we could insert more atoms in the interstitial spaces. Yes, we could do that. So therefore you would see this is one atom we have inserted over here, exactly the way over here. You see that this is the normal cube, the body-centered cube when we added one atom in the center, and now there are spaces on the faces. This is the face of the cube. The face of the cube is this one. You see how many faces are there? There are 6 faces, 1, 2, 3, 4, and the front and the back. This is very, very important. Can you count the 6 faces of the cube? So cube has the 6 faces. If the cube possesses 6 faces, it means there is a possibility of 6 atoms can be introduced on each face. 1, 2, 3, 4, and this front and the back. So 6 atoms can be included. Now the same is the story for this one. If I'm going to take out this razor sharp frame out, and this is the unit cell structure for the simple cube, what would be the unit cell structure for the body center? So this would be the body center cubic unit structure when I'm going to snatch out the frame. You see there is a full-fledged atom, and that atom is exactly in the center, hence that is not going to be affected when I'm going to take the frame out. Okay, now we need to quantify that how much area of this one atom, because that is exactly same in all the cases, how much the surface area of the atom is included in the unit cell. That we can calculate easily in by putting the atom, all the layers of the atom in 3 dimension. I have only shown one atom, but you could imagine there are atoms over here, here, above and below, and there are layers running above and below. So it means that if I'm going to erase the layers and only showing the frames, it means the atom that is at this position or this position or on this position, all these atoms all these atoms are in fact contributing to eight cubic structure, 8 cubes, 1 2 3 4 5 and 4 is below. So 8 cubes, this corner in fact is the common corner that is being occupied by an atom, and that atom has embedded some portion of its surface area in 8 cubes, and therefore it is shared by the 8 cubes. So therefore when the area is shared by 8 cubes, so then we can say that one atom, so it is shared by 8 cubes. So therefore the surface area of 1/8 is included in one unit cell. So it is the unit cell. So 1/8 part of one atom is included in the unit cell. But that is the case when you have the simple cube. It is not the situation for all the other cubes like the body center or the face centered cubic structure, but this is only for the simple cube. Realized that there is one atom on the face of the cube. There is no issue for this because it is already inserted in the center of the cube. So therefore, the one full-fledged atom is already in the cube. But what is the area when an atom is going to be placed on the face, and how much area of it is going to be included in the unit cell? So you see, this is one cubic unit cell. There is another cubic unit cell. They have the common face. The common face because they are attached to one another. So therefore this face belongs to this as well as to this one. So therefore the atom that is possessing this face is half of this surface area is included in this unit cell and half in this unit cell. So therefore when the atom when the atom is placed at corner, which is also known as vertex, then 1/8 part of the atom is in the unit cell, and when the atom is on the face, side face, then half of the area is in the unit cell. Can you make out that? I don't need to explain it because the diagram itself is showing this. So you could see that there is half of the atom in this side and half of the atom on the other hand side. Okay. What is the meaning of this whole story? We are heading for the quantification. So therefore, we need to know that how much surface area of the atom is included in the unit cell. In 3 dimension, you could see this. There is a 1 cube, second, third, fourth. Likewise, there are 4 cube of the lower layer, and it means that this much part of the atom which is shared by 8 cubes is 1/8 that I have explained over here. and when the atom resides on the face, that is being shared among the two cubic unit cell. The half of the surface area is included in the unit cell. So for the body center, I have explained there is just one full-fledged atom in the unit cell. Now, if someone asks you that I can understand that there are 1/8 part of each atom included in the unit cell, then how much is the total surface area that is included in the unit cell? So you will find that the cube is you will find that cube has 8 vertices. There are 8 positions. So therefore there are 8 atoms. So the surface area included in unit cell. So there are 8 atoms, and each atom possesses 1/8 part. 1/8 part. Each atom possesses 1/8 part or includes 1/8 part in the unit cell. So therefore, I have total surface area equal to 1 atom. Is it okay? The total surface area, it means that the total surface area of all the 1/8 atom, 1, 2, 3, 4, 5, 6, 7, and 8, the total surface area of the atom that is embedded inside the simple cube is equivalent to 1 atom, right? The total surface area. So try to understand the language I'm using, because that is very, very important. The total surface area is equivalent to 1 atom. If somebody asks you, I have read somewhere that the unit cell possesses 1 atom, you will say, no, that is not correct, the way of explaining that. The unit cell cannot be made with just 1 atom. The surface area of 1 atom obviously can be included in the unit cell, and the unit cell can be made from the 1/8 part of 8 atoms equivalent to 1 atom. That is the meaning that the surface area is included for 1 atom. Okay, now how many atoms equivalent surface area is included in the unit cell of body-centered cube? So I have 8 atoms exactly way the simple cube, 1, 2, 3, 4, 5, 6, 7, 8, and there is 9th atom in the center. 9th atom in the center. So what I can do, it means that 8 atoms are equivalent to 1, equivalent to the surface area of 1 atom, plus there is 1 atom. So the total surface area is 2 atoms for body-centered cube, unit cell. Is it correct? So this is the body-centered unit cell. What is the situation for the face-centered cubic unit cell? And you see, there is none in the center, but all the six on the faces. So it means that I am still taking over here, plus 6. Each one is contributing half. So therefore, there are 3 atoms, surface area, plus the 1. So therefore, for face-centered cubic, 1 atom from here, from 4 atoms, 1/8 part, plus 3 atoms, total is 4 atoms. So 1 atom for the simple cube, 1 atom, body-centered cube, 2 atoms, and face-centered cube, 4 atoms. Is it okay? So, if someone asks you that which is the compact atomic arrangement in the crystal lattice, lattice means the crystal 3-dimensional structure. We in solid state chemistry, we use the term lattice, crystal lattice, and you will be saying that the unit cell that contains greater number of a higher surface area equal to the greater number of atoms, that is the most compact arrangement. So therefore, among these three, the face-centered cubic geometry and the unit cell, so that has the maximum compact arrangement, and there are practically negligible amount of the interstitial spaces. And for the body-centered cube, still there are interstitial spaces, whereas in the case of simple cube, there are plenty of interstitial spaces. So in this way, we can differentiate. So this is the fundamental definition of the solid state, and we will only focus our attention on the cubic structure. And suppose if you ask me, this is the unit cell for a crystalline structure that has the cubic structure. And the straightforward question is that what is the unit cell structure for the crystalline gold nanoparticle, crystalline silver nanoparticle? The crystalline gold and the silver nanoparticle, they have the face-centered cubic geometry, right? And therefore, the arrangement in the gold atom, in the unit cell, which you will expect, should be like this. Not like this or this, but so it's a very compact arrangement in the case of gold, silver, kind of noble metal nanoparticle. We are coming to the iron oxide nanoparticle. First, I'm going to explain this. Now, there is a way, suppose now we have realized that the face and the cubic unit cells are like this. Is there a way, suppose if I know the size of an atom that is making the unit cell, can I predict without performing the experimental measurement, can I predict that what is the size of the unit cell, what is the size of the cube? Or size of the cube means because all three sides of the cube, they are equivalent, so therefore I need to calculate the one side of the cube, that is known as edge length. In the case of cube, right, this is the edge, right? This is the edge. This one is vertices. All the corners are the vertices, and this is edge. And this represents the length, one side of the cube. So therefore, this edge length is related to the radius of an atom. So without performing the measurement, if you know that a particular crystal is made up of this kind of atoms, and the size of the atom is, the radius of the atom is this much, you do not need to measure the XRD or other measurement to calculate the dimensions of the cube. Simply on the basis of quantitative treatment, you will be able to calculate the edge length or all the lengths of the three sides of the cube. So now in the case of simple cube, you see that the surface of the atom that is placed on this corner and the other atom that is placed on this corner, their surfaces, they are touching each other. So the surface of this and this, they touch over here. So therefore, the radius of this plus the radius of this, that is the edge length. I can say this is the edge length. I can say it is A because they are all equivalent, and that is equal to 2R. In the case of body-centered cube, that is not the case. In the case of body-centered cube, the surfaces which you see, they are touching over here, that is not the case. So there is a space over here. So therefore, you cannot use that formula right away to correlate between the radius of the atom and that of the edge length. And then you have to take another mathematical treatment, that is the we can draw a simple triangle with the 90-degree angle, and this one is hypotenuse. We know that this side of the triangle, the square of hypotenuse is equivalent to the square of the base and the plus the square of the other side, right? And here, what we can do, we can keep this as a triangle. This is one side, this is one side, they are equivalent, right? So the b square is equal to a plus a square. This is one triangle. We can have another triangle, and the triangle which we are drawing, so this is one side, or you may say the base of the triangle. This is the side of the triangle, but the hypotenuse in this case, that is running from this corner not to this corner, because both corner are on one side of the face. This line is running from this corner to exactly to opposite, diagonally opposite corner. So therefore, it is running through the central atom. The atom which is in the center, this line is running through the central atom, reaching to the other opposite corner, right? So, and you will see the sides of all the atoms, the one this is touching the side of the atom that is placed in this center, and the side of the central atom is again touching over there. So this is R, this is 2R, or the d diameter of an atom, because the line is tracing or running through the atom from one side to another. So therefore it's 2R, and there is another R. So therefore what we can say is c square is a square plus b square, right? And now I have three a squares. I can add them, right? And I can substitute the b square over here. C square is equal to this, rearranging it. And so I have a related to the radius, edge length here, that is related to the radius through this formula. Now you will see that this formula is much complicated in comparison to this. Likewise, you can do it by drawing the triangle over here. So these are the relationship between the edge length and the radius. I mean to say that if you know the crystal structure of the unit cell of a crystalline solid, right, and if you know the radius of the atom, plug it over here, the value, radius of the atom, right way you can calculate the edge length. You can say that the unit cell edge length is this one. Likewise, the unit cell for the edge length for BCC, you can calculate like this. You can perform the simple calculation. Mathematically, that's not a big deal. For the gold atom, you can see that what should be the edge length for the gold nanoparticle FCC structure. So you'll be putting the radius of the gold atom over here, and you will be able to calculate the edge length. Now, apart from this quantification, there is another relevant more quantitative parameters which we can calculate: mass and the volume. Suppose if somebody asks you, this is the unit cell for the face-centered cubic geometry like that of the gold nanoparticle. What is the total mass of the unit cell? Here we have not yet talked about the total mass. If we can calculate the total mass, obviously mass can be related to the volume through the density. Or if we have the volume and the mass, we can calculate that what is the density of the unit cell. So that is what I have shown it over here. Calculate the mass of a single aluminum unit cell. So mass of the entire aluminum unit cell. So for the color contrast, this atom has a different color from this atom, but in fact, as long as we are talking about the pure aluminum, all are the aluminum atoms. In North America, we call aluminum, and here in India, we call aluminium. Do not get confused. Aluminum and aluminium both are the same thing, only the way we name it. So it's a face-centered cubic geometry. So for the face-centered cubic geometry, we know there are 4 atoms, and it means that in order to calculate the mass of the 4 atoms, we need to multiply the mass with the formula mass. But you know that the formula mass is gram per mole. It is not the formula mass of one atom. It's the formula mass of 1 mole of an atom. The definition of a mole is the number of atoms equivalent to that of Avogadro's number. So it means that if you need to calculate the mass of a single atom, it means that you have to divide this formula mass of aluminum with the Avogadro's number per mole. You must cancel the unit with the unit, and eventually you should have the answer in grams. So this is the mass of a single atom. Since there are 4 multiplied by 4, this is the total mass of the unit cell. So what if we want to calculate the volume and the density, right? So here you see, calculate the density of potassium metal if the edge length of the body-centered cubic unit cell is 535 picometer. Okay, so it's 534 picometer. Edge length is provided. You have to calculate volume or the density. It is much straightforward to calculate the volume because all sides of the cube, they are equivalent. All sides of the cube, they are equivalent. So therefore, if I have to calculate the volume, simply I need the length of one side and I can take the cube and that would be the volume. And that is what over here. So edge length can be represented by A as I've shown it uh, over here, or it can be represented with L. The different textbook follow different way of depiction. So you don't need to get confused as long as it is representing, it's saying that it's the edge length, no matter it is being represented with A or L, it means that it is the edge length. So here it is represented with L, it is L not 1, right? So L cube, so it is in picometer, 10 to the power minus 12. Why we need to convert the units? The thing is the density is in centimeter cube, gram per centimeter cube or gram per ml. So therefore you have to convert the units. So you are converting the picometer into centimeters. So picometer into centimeter and then taking the cube and eventually this is the volume. You have the volume and now in order to calculate the density, you need the mass. The way you calculate the mass over here, the same way you are going to calculate the mass over here, but this is body-centered cube. Keep one thing in your mind that most of the exam questions, they will not tell you that how many atoms are included, how many atoms equivalent surface area is included in the unit cell for the simple cube, body-centered cube or face-centered cube. This you have to decide, right? So therefore, I mean to say that as you could see over here, it is saying the mass of a single aluminum unit cell, but it's not. It is saying that it exists in the FCC, that's the face-centered cell, saying that how many atoms, equivalent surface area is included in the unit cell of FCC. This you need to know that if it is one atom, four atom, or the two atoms. You got my point? So very important because most of the question will never tell you that how much surface area equivalent atoms included in the unit cell. So that is the case over here. That's what I'm saying, that you need to figure it out that how much is the surface area. It's two atoms, right? We've already talked about. So two atoms. So when you are calculating mass, you must be multiplying with 2 because the body center cubic unit cell not by the 4. It's not by 4. It must be with the 2 when you are dealing with the BCC body center cubic cell. Now you have volume and the mass and you can calculate density. Make sure that all other units are cancelled, right? Coming back over here, so basically it's mass by the volume, so therefore no unit is going to be cancelled, but you must take care of the final units, gram, centimeter cube. So therefore density must be represented with the conventional unit, so it is gram, centimeter cube or gram, so that is the case. But here we can ask. So you should take that the density should be represented in gram centimeter cube. For that of the silver units. As I told you that gold and silver metallic like crystalline pieces in any form in nanoparticle as well is the FCC unit cell. So therefore it is the same story over the same kind of calculation but with different number. Yeah. So we have completed the basic definition of the crystal structure and the quantification. Look at all the slides or what we have gone through. If you have any question before I go ahead, because the next part is what I say. It is what we have till now understood or explained. So it is the self-test which we will go through in the next slides. If you have any questions, you can ask me. Okay, realize that we are heading to understand the crystal structure, unit cells of the ionic compounds, and how the unit cell of the ionic compound is related to the molecular formula. Now, somebody asked you that I cannot understand that when we write the molecular formula of oxygen O2, carbon dioxide CO2, it represents the single molecule, right? But when we write the molecular formula of sodium chloride, the salt which we use every day, and that is also represented with a single formula, and on the other hand, sodium chloride exists in a crystalline phase where sodium chloride is repeating itself in 3 dimensions. Then the answer is over here. Whenever the crystal structure you see for any salt, and the unit cell of a salt means, salt is a common term to be used for electrolyte, which is made up of 2 oppositely charged ions in any different ratio. Here you will see that cesium chloride, 1 cesium atom in the cationic form combines with the chlorine in the anionic form. Cesium chloride, the cesium cation, chloride anion, likewise the zinc sulfide, and then you see over here we have 2 fluorines for 1 calcium, right? Or 1 calcium cation, we have 2 fluoride ions. How can we derive the formula from the unit cell? It means that as we mentioned, as we have understood now, for any crystalline structure, the unit cell repeats itself. It means the unit cell should represent this formula, because this formula is repeating in 3 dimensions. So therefore, the unit cell must represent this formula. Okay. Now we will try to see if really the unit cell repeats this formula for the cesium chloride. Okay. So I have the unit cell is made by how many cesium cations are making the unit cell? How many? 8. Correct. So there are 8 cesium cations. How many chloride anions are making the unit cell? It's 1. Okay. Now, if you look at simple 8 to 1, you cannot figure out the formula. That's the confusing. If somebody say, no, cesium chloride unit cell is made by 8 cesium cations and 1 chloride, we cannot settle with the cesium chloride formula that is shown over here. Then, which is the correct way to represent that? So, it is not the 1 cation's total surface area that is included, right? So, how much that is? 1. So, it is 1/8 part. So, it means that 1 one cesium cation is there. So I can write one, sorry. So, here, one cesium, and it, no, we should write it like this. And how many chloride? One. That is exactly embedded in the center, and therefore its total surface area is equal to one atom or one anion. So therefore I can say, writing the chloride again 1. So when we have to write the formula for an ionic salt, make sure you understand that ionic salt always exists in the fully neutral state. So then you are not supposed to write the charges. So it is automatically understood that it is one positive charge, and there is one negative charge, and the overall charge is 0. So electrical neutrality is established. So therefore, when we have to write it, we will write cesium chloride. We will not write the subscript. Right? It is automatically understood that one positive charge is balanced by one negative charge. That is the meaning of this formula. So this is the way we draw it. Now we have to prove that the zinc sulfide, this is the unit cell for zinc sulfide. So I'll give you 2 minutes or 2 or 3 minutes to prove that you really, the way you have come up with the cesium chloride formula, the same way you can come up with the zinc sulfide. Go ahead, please. Do it on your paper. How many sulfide ions are there? Where are they? And how many? You can take 2 minutes time, and then I can ask. Okay, so how many zinc ions are there? There are 8 zinc ions at the vortices, and each one is contributing 1/8 part. So therefore, 1 ion is at the vortices. There are other 6 ions at the faces. You see the 6 ions? So this is the face. 1, 2, 3, 4. This one is the front face. This one is the back face. Cube has 6 faces. Okay, so therefore 6, 1/2 is contributed. So there are 3 ions total. Zinc. So that has 4 ions. Now we come to the sulfide ions. How many are there? All the gray balls. Gray balls 1, 2, 3, 4, 5. 4. Inside, on the face, or outside? It is much easier to understand the atom is exactly at the center, but when it's slightly, okay, Is it sp3? Which one is this? sp3. And is it octahedral? So tetrahedral, correct. So when it is, this one is tetrahedral. It means there are 4 connections. You see, for the tetrahedral, the central atom is connected to the 4th position tetrahedrally, and usually the bond angle is 109 degree, as you could see in the case of methane, right? And therefore, this position is on the corner, this position on the face, this position on this face, this position on this face. It means there is no way this atom or the ion could be away from any of the 4 positions, means exceeding the side of any of the 4 positions. It is somewhere in between the 4 positions. So therefore it is in the unit cell, right? So therefore how many? So there are 4 ions. Now you can place this zinc 4 subscript representing the 4 ions. Likewise sulfide 4 ions, and I have to depict it as a completely neutralized form. So it is 2 multiply, I can say 4 multiplied by plus 2 plus 4 multiplied by 2 minus exactly 0. So therefore I think sulfide like this. You don't need to show the charges. You don't need to show how many atoms. Molecular formula for the sulfide that is repeating itself. Right. The name of the unit cell is cubic. This is the common name. If somebody asks you what is the zinc blend, you may say because it's a common name for this salt unit structure, but the actual name is the cubic structure units. Potassium fluoride. So, again, how many calcium? Exactly the way we represented zinc. So the same positions are occupied by calcium. So at one equivalent surface area for all the 8 vertices, there are 6 positions and contributing 3 atoms. So therefore, I do need calcium 4 ions. Okay. Now, fluoride, how many ions? 8. And what is the bonding or what is the geometry for the fluoride ion tetrahedral again? Right? So therefore, inside the cubic structure. So therefore, you will say there are 8 ions. So I can say calcium 4, fluoride 8. Whenever you have something like this, the numbers which you can divide by the common factor, you must divide them to come to the undivided form. So therefore, it is calcium. If I'm going to divide with the 4, it is 1 by 2, right? So now, can we get the neutralization of a charge? See over here. It's 1 multiplied by plus 2 plus 2 multiplied by minus 1, right? So therefore, it is 2 minus 2, 0. Is it okay? Charge by taking 2 fluoride and taking 1 calcium, only then we can neutralize the charge. And that is why the formula is calcium fluoride. You do not need to show the charges. Okay. So what I want to say that you can have more practices by picking more unit cells, structure for different ionic compounds from the internet, and you can practice by yourself. So we are done with the basics of the crystal structure, and we will see that how we can apply it to the focus. Our Gyan code. Try to see. Now going ahead with this, how can we differentiate covalent crystal or the crystalline from that amorphous? The most prominent example is the diamond and graphite. Right? Both are made up of pure carbon atoms. The one is crystal, other one is graphite. Somebody can ask you, what is the problem? Diamond is clear crystal, graphite is not, right? And where is the problem? So can you tell me that what is the geometry for the carbon in diamond, and what is in the case of graphite? Tetrahedral in diamond, and in graphite okay, this is methane, this is ammonia. What is the geometry for the methane? What is for ammonia? No. I'm saying what is the bonding structure, Lewis structure for that of ammonia? Pyramid is the shape, not the geometry. When we say geometry, it means that you have to name the geometry. So tetrahedral is the right, and likewise for ammonia, what is the geometry? Again tetrahedral. Which one? Okay. Why we have straight tetrahedral in both cases? There is no bonded position. Here you have the bonded position. But when we do not have the bonded position, can't be it sp2 because there are three connections, there are three bonds. So it means that the central atom, whenever it is possessing the lone pair, 1, 2, the lone pairs are counted as the bond positions, right? Do not exclude them. So it means that there is a fourth position available, though it is not occupied, and that is why still it is sp3. But here, do you see something like this or not? Do you see the lone pair on the carbon in the case of graphite? No. So, it is sp2 hybridization. It's a triangular planar. You see the triangular planar? That is the shape of the molecule, right? This one is tetrahedral, and the bond angle. What is the bond angle for the triangular planar? How much? 120, correct. So, in fact, these are the layers, and you might be remembering when there is sp2, right, and there's a fourth position which exists in the form of pi bond, right? So that is what over here. The one layer below, and there is another layer, so they slide one above the other, so therefore these positions are not fixed, right? When these layered positions are not fixed, they slide one above the other, so therefore you cannot have a crystal structure. In the form of crystalline form, it is the amorphous. Okay? So this is the right way, the correct way of evaluating it. Molecular crystals, you know, they are soft like sugar is a molecular crystal, right? So here we were talking about the most of the time the ionic crystals here. And then it's a metallic crystal. So metallic crystal, all transition metal. So there is a mobile electron. See, they are the fixed positions, right? And these fixed positions as indicate gold. So that is the FCC structure. So this is the comparative physiochemical properties: ionic, covalent, molecular, and the metallic. And the general properties and the examples are over here if you want to compare them. I'll take another few minutes. So glass is also the one glass. It is not the condition that if the light runs through the solid substance and that could be a crystal. That is not the condition, right? Light can run through the window glass, but the window glass is not a crystal. It is amorphous, right? So therefore that is not a condition. But most of the crystalline substances, you can see through them, but that is not a blanket statement. Okay, so in the case of glass, silicon oxide, when it's quartz, that is on the fixed position, only then it's crystal. Otherwise, the normal glass is not a crystal. So in conclusion, what we have learned today, the difference between crystalline and amorphous solids, that was the main discussion. We started from, our focus was on the crystalline solid, and then the crystalline solids, we wanted to quantify them by defining the unit cell. Our focus was on the cubic unit cell, and because the cubic unit cell is one of the most prominent, important unit cells that is possessed by the gold and the silver nanoparticles. And then we talk about the quantification of the solid, I mean density of the unit cell, the mass of the unit cell, and all other properties, how we can relate the unit cell with the radius of an atom. Thank you so much for your attention, and if you have any questions.